When we discuss wide area networks in this course, and believe me, we will, we're going to run into quite a few different encapsulations. We're going to have HDLC, frame relay, and the point-to-point protocol in particular. If you don't know what any of those three are, don't worry about it. We're going to take care of that. But right now I want to concentrate on local area networks, and whether we're connecting a host to a switch, or we're connecting two switches, or we're connecting a switch to a router, we are very likely using Ethernet and Ethernet cables. And in this section, we're going to talk a little bit about how Ethernet works. There'll be a little bit of that in the switching section as well. But here we're also going to concentrate on the different types of cables we use in a network. And note that I said cables with an S because not all Ethernet cables are the same. And actually, not all Ethernet types are really the same either. So we're actually going to start there. Ethernet is really an umbrella term. We do have a specific standard that is just called Ethernet, but we also have fast Ethernet and gig Ethernet and 10 gig Ethernet. But when we discuss Ethernet, that again is like an umbrella term. We're really talking about all of those. So we've got several different types of Ethernet with different capacities and different challenges. And for both a successful exam experience and a solid networking career, we need to be comfortable with these values. Now, most kinds of Ethernet cables are unshielded twisted pair, UTP, and the name is indeed the recipe, because the wires inside the cable itself are indeed pairs of twisted cables. It's not just one wire going across. That's all we see because you see the outside of the cable when you pick one up. But there are wires inside, and when you're using UTP, they're actually twisted. They're pairs of twisted cables. Now, of course, the first question would be, why do we do that? But the answer is already on the board. Twisted pairs of wires inside the cable really cuts down on electromagnetic interference, EMI. Now, EMI can interfere with the electric signals being carried by the wires, which in turn is really going to screw around with our network. EMI can come from a couple of different sources. It can come from other cables, which is why you don't necessarily want to tie 50 cables or 100 cables together with one wrapper, if you could. And infamously, it can also happen from with elevators, because when certain buildings I've been in over the years, they would run their cables from one floor to the other right next to the elevator. And at lunchtime, quitting time, for most of the people, that's when the elevators were in heavy usage, and literally you'd see the network start to slow down because the cables were right next to the elevator shaft, and that in turn gave our network the shaft. Now, we can have EMI problems from other wires in the same cable. This is called crosstalk, and it happens when a signal crosses over from one pair of wires to the other, and what in essence that does, it makes a signal on both sets of wires unusable. Now, near-end crosstalk next generally occurs when wires are crossed or crushed. The conductors inside the wires don't even have to be exposed, but if the conductors are too close, again, the signal traveling on one wire can interfere with the signal on another wire, which is why when I taught one class for high school students about making your own cables, this is a long time ago, and they liked that part, but it's like, let me see how many times I can walk on the cable and still have it work. So don't walk on the cable. Now, here are some common Ethernet types that run on regular old copper cabling, and I've given you their official IEEE name and the more common name for them. All of these Ethernet types have a maximum cable length of 100 meters. It is a good idea to know these standards by number, say with Ethernet standard being 802.3. We usually call that 10 base T, and it runs at 10 megabits per second. Fast Ethernet, 802.U, usually referred to as 100 base T, runs at 100 meg. Gigabit Ethernet, even better, 802.3 AB, is generally called 1000 base T and runs at 1000 meg. 10 gig Ethernet, 802.3 AN, is not called 10,000 base T. It's usually called 10 G base T and runs at, you guessed it, 10 gig. There's a really big difference in speed between 10 gig base T and 10 base T, obviously, so you definitely want to watch that G. Now, copper cable is not the only kind of cable we have out there in today's networks. We also have fiber optic cable. There's a version of Gig Ethernet that runs on that. It's 802.3Z, and that's often called 1000 base LX. Now, this version has a max cable length of 5,000 meters, and that's as opposed to 100 meters for everything else we've looked at so far. So this sounds like a trick question, then why aren't we all running 1000 base LX? And the reason is cost, because the fiber optic cable is still a lot more expensive to install and troubleshoot than copper cable. I've been in situations in labs where you suspect it's the cable, you've checked everything else out, and you just swap a cable out. Well, the sheer cost, you're probably not going to have fiber optic cable sitting around your lab for you to swap out. It's still pretty expensive to run fiber. Now, let me go back to that previous screen. I did have something else for you. I got cut off. Multiple standards usually equal multiple nightmares, and luckily, this is not one of those situations. Because usually when you mix flavors even of the same kind of thing, like say Ethernet, we've got Ethernet, we've got Gig Ethernet, we've got Fast Ethernet, it sounds like we're going to have trouble sending Ethernet frames across a link or across a network if it's going to go on regular Ethernet for part of it, and then Fast Ethernet, and then Gig Ethernet, and then back to Fast Ethernet. But when you send an Ethernet frame from point A to point B, thankfully with this kind of situation, we don't have to do some kind of translation every time the frame goes from Ethernet to another frame, to Gig Ethernet and then to Fast Ethernet. That'd be doing a lot of translations, and of course would be adding big time to our transmission time and overall network workload, because all of our different Ethernet standards have the same overall frame format: header, data, trailer. That's it. And there's just a little bit of detail we're going to look at later in this section, but I wanted to bring this up now just to let you know this is why we don't have a lot of trouble mixing our Ethernet speeds and capabilities. There's another tool that allows us to seamlessly use network and host devices with different Ethernet capabilities: Autonegotiation. And if you're an experienced network admin, you've been around for a while, you're probably already rolling your eyes, right? Because I admit, I just like, oh man, that stuff never works. Well, Autonegotiation has a bad name because it didn't really work all that well years ago. And it really got to the point where a lot of network admins, yours truly included, would just manually set your card and port settings. And Cisco went so far as to make it a best practice not to use Autonegotiation, and some other vendors did too. Now, I mention this now because I don't want you more experienced network admins kind of glossing through this or going up to get coffee while I'm talking, saying, that doesn't work. Autonegotiation has actually come so far since the bad old days that it's actually mandatory for Gig Ethernet over copper, and it's an important part of the overall Gig Ethernet standards. It's also going to be an important part of your CSense and CCNA exams, so we ought to know what's going on here. Now, in this example, we've got a host device connected to a Cisco switch port, and the host is running 10 base T, and the switch port it's connected to has a top capability of 1000 base T. So how do the devices talk to each other in the first place and let each other know, hey, here's what I can do. Here's my duplex capability. Here's my speed capability. Well, they do that via the Fast Link Pulse, FLP. And you're likely thinking with that name, well, fast is compared to what, Chris? Well, fast is compared to the normal link pulse, the NLP, of course. Basically, the NLP is sent by an Ethernet device when it doesn't have anything else to send. It's like basically saying, hello, I'm still here. And this is a concept we're going to come back to over and over again in networking, because it's very rare when you set something up, whether it's Ethernet, whether it's your Cisco switches, whether it's your routing protocols, whether it's an advanced routing technique you're using, you're almost always going to have some kind of hello. Like, hello, I'm still here. Hello, this operation is still working. And that's what NLP really does for Ethernet. Compliments of Wikipedia, here's the NLP. And don't sweat the numbers. I really just want to show you the comparison between the NLP and the Fast Link Pulse. And this is the normal link pulse. Now, the Fast Link Pulse, and that's what all Autonegotiation-enabled devices use to announce their capabilities, looks something like this. So you can see that a lot more pulses are being sent in a 2 millisecond period of time, and that is very fast. We are not going to get into the ultra nuts and bolts of how they do that and the voltage changes, everything else. It's way beyond the scope of the exam, but Wikipedia does have a good page on that if you want more information. Now, after the devices exchange this information, we've got a host saying, hey, I can run at 10 meg full duplex. the switch port is saying I can run at 1,000 meg full duplex. They decide on the best values to use. Now, as you would expect, the lowest speed is the one that's going to be selected. Also, full duplex is always going to be preferred over half duplex. And in this situation, the PC port and the switch port it's connected to would agree to run at 10 meg full duplex. Now, another concept I want to introduce you here to early on is letting the switch and the router do the work. It's not being lazy, it's being smart. And by that I mean, if you statically configure every port on a Cisco switch with your speed and your duplex settings, what happens if they change on the other end? Well, if you swap PCs out and you've got, say, a faster PC, or for heaven's sake, you got a device that runs at half duplex, you have to remember to go on the switch and say, okay, I got to go to that port, and I've got to do this, and I've got to take care of, changing these settings. That doesn't sound like much, but it adds up, and we have enough to do. We're going to let the switch do the work. Now, Autonegotiation is going to dynamically adjust if a port capacity changes. And let's say you replace that PC with a PC that can run at fast Ethernet speed. And in this situation, the PC is now announcing, well, I can run at 100 meg full duplex. And the switch port is still saying I can run at 1000 meg full duplex. Again, if we manually set all of our port settings, we're going to have to change the speed on the port manually, and we're going to have to maybe change the duplex. We wouldn't have to in this situation. And you know what else is really easy to do? It's really easy just to get the wrong port and change the wrong setting. Because sometimes, if you've been in a crowded closet, and you got all these switches in here, and you got all the wires, and you're trying to trace the one wire that goes to that one particular port, that can be a bit of a nightmare. And even if you use another tool, which we'll look at in the course, called Cisco Discovery Protocol, to find out which port it's connected to, it's just really easy to make a mistake. What you're doing is playing the odds. The more information you enter manually, the bigger chance there is that sooner or later you're going to enter a wrong number or just set a speed incorrectly. So again, let the switch do the work with Autonegotiation. That is a really sweet feature. Now, I highly recommend, and I think Cisco will agree with me on this, I highly recommend that you use Autonegotiation on both ends of a link, such as the one we just looked at. Use it on both ends or don't use it at all. I hope the only scenarios you ever see where you're using Autonegotiation on one end and not on the other are on a practice exam or on your real exam. Because what happens is you can end up with a link that isn't working at its true capacity due to what we call a duplex mismatch. And that's a link where one endpoint is running at half duplex and the other end is running at full duplex. When you're using Cisco switches, if Autonegotiation is turned off on the other end of the link, the switch should still be able to sense the speed capacity of the other endpoint. Now, if for some reason that speed capacity can't be detected, the lowest speed supported would be used. That probably doesn't surprise you, but here's something that might surprise you. If that detected speed is less than or equal to 100 meg, the switch is going to set its port speed to half duplex. And then you've got a duplex mismatch. Now in this particular example, make sure that's all on the board, the Cisco switch has successfully detected the capacity of that remote endpoint to be 100 meg. No problem there, because we're running 100 meg full duplex, not running Autonegotiation on the host, 1000 meg full duplex and running Autonegotiation dropped an end there, but that's okay, on the switch. Now, the problem does arise when the Cisco switch sets its port connected to that host to half duplex as a result of that speed of 100 meg. Because again, if the detected speed is 100 meg or lower, the switch will set its port speed to half duplex. Now, you may be thinking, is this really that big a deal? And the answer is yes. It is a giant pain in the behind, and let me tell you why. They do have a special place in network hack. Because when we go through this course, when we have mismatched settings on two ends of a communication, we'll see this with some of our wide area network protocols. You've got point A doing one thing, point B doing another. Most of the time, what you will have is just a downlink because they don't agree on something. If two ends of a point-to-point protocol link do not agree on certain values, the link's just going to go down. And that is really easy to spot. It's like, hey, I looked at the router, looked at the switch, this link's down, we got to fix something here. Here's the trick with a duplex mismatch. In this particular scenario, the link between those two devices would not go down. It's going to stay up. But the problem is the transmission is going to be a nightmare, because you're going to have one end of the communication that can send or receive but can't do both at the same time. And you end up with something we call false collisions, and it's just going to be a real nightmare. You don't want this. But the problem is, again, it's not like you're going to look at the router and say, or the switch and the host and say, oh, okay, this link is down, because the link is going to show as up. But what you're going to hear are complaints, hey, this communications aren't going through, etc. And that is the result of a duplex mismatch. So again, outside of an exam, I don't think you're ever going to run into a situation where you're running auto negotiation on one end but not on the other. But you're likely to see one in your exam and in your prep. So just watch out for that. Again, the link's going to be up. It's just that the data is not going to flow correctly, because again, you got one end of that channel that can send or receive but can't do both simultaneously. That's what half duplex is. Let's see, what do we got coming up here? We're going to talk about our cable types next. Yes, starting with crossover and straight through cables, and we're going to start that on the next video. I'll see you there.